Hi, kids. It's Tuesday. It's May 5th. And today I want to briefly go over the Earth's mantle slide activity that I had you complete last week. So, the focus this week is on the Earth's mantle and probably a little bit into next week because the mantle is a really significant portion of planet Earth. And there's some really cool things happening below our feet in the mantle that are really important for you to understand as we move on to talking about Earth's tectonic plates. So let's do just a quick review of what the mantle is. So the mantle is the thickest section of planet Earth by volume. It takes up most of planet Earth, about 83% of Earth's volume, and 67% of the mass of planet Earth is the mantle. So I like to think of the mantle as analogous to the white of a hard-boiled egg. You know, that the white of a hard-boiled egg takes up most of the egg, and it's a good analogy to Earth's mantle. Now, Earth's mantle is definitely slightly denser than the crust that sits above it. The average density of the entire mantle is about 4.5 grams per cubic centimeter, and that means that there's 4.5 grams of matter stuffed into every little cubic centimeter. In fact, let me show you what a cubic centimeter looks like in my bag of goodies here. So I'm going to hold up a little cube, and you should be able to see that. That right there is a cube that measures 1 centimeter on each side. That is 1 cubic centimeter. So something that has a density of 4.5 grams per cubic centimeter, I want you to envision 4.5 grams of matter in this 1 cubic centimeter. And that's how dense the mantle is on average. Now, that doesn't seem very dense, but comparatively to the crust, it is slightly denser. Remember, the continental crust, which is composed of this light-colored, bedazzled, and speckled rock granite. This has an average density of 2.7 grams per cubic centimeter. And then we have this dark-colored rock. This dark-colored rock is basalt. This is the oceanic crust. This is the chief bedrock of the ocean crust. This has an average density of 3 grams per cubic centimeter. So think of 3 grams of matter jammed packed into every cubic centimeter of this rock. And there you have the density of basalt. So we have granite being less dense. It sits on top of the basalts. We have basalt being more dense. And then we have the average density of the entire mantle, even denser than the ocean floor. And that would be about 4.5 grams per cubic centimeter. Now, what's really cool is the mantle is made up of this really cool rock called peridotite or peridotite. Some people like to pronounce it like that. And the word comes from one of the chief minerals that makes up the rock, peridot. Peridot is a real green mineral. It's actually the birthstone of August. So if you were born in August, you have this really beautiful lime green, light green mineral called peridot as your birthstone. And it is a mineral that's made up of another mineral called olivine. And in my hand, I went rock collecting this weekend for you guys. Went to a little local rock store and picked up this sample of peridotite, and you can see that it is a lava rock, really. All right, and it's really, really dense. And that lava rock has a lot of iron in it, but it also has that cool mineral, olivine, that shows itself as the gemstone peridot. And so if I look and turn this so that you can really see this, you can see that green, shiny, beautiful mineral on the peridotite. Guys, this is super, super heavy. I have to tell you, this rock for its size is really, really dense. This is a perfect example of a rock that would come from the mantle. Now, how do we get these mantle rocks? We've never drilled to the mantle. We've only touched the surface of the crust as we're drilling. These type of rocks actually come up from the mantle through volcanic eruptions or volcanic intrusions, sometimes they're called. So this is just a sample of the peridotite that is really representative of the Earth's entire mantle. Scientists really believe that this is the rock that represents most of the mantle, and it's more dense than both the ocean crust and, whoop, can I get all three in my hand? The continental crust. All right. So remember, the Earth is layered because of density differences between the layers. And those density differences are really dependent upon the composition of the layers. The layers are composed of or made of different rock. So this peridotite is a nice representative of the rock of the mantle. Now, the mantle is composed or broken into three unique parts. The uppermost mantle, which sits right beneath the crust, the entire crust, both the continental crust, that thick portion of the crust that has the mountain ranges on it, and the thin section of the ocean floor. Right below that is the uppermost mantle. It is solid and rigid, just like the crust, yet it's composed of that slightly denser peridotite. And together, the uppermost mantle and the crust make up one of the first physical sections of planet Earth, kids. And we call that physical section the lithosphere. Now, what I did here was I took the chart that I had you fill in and I broke it up into just three nice slides. So the uppermost mantle, that first section of the mantle that lies just below both the continental and the ocean crust, is solid just like the crust. Together with the crust, make up the lithosphere. This is the thinnest section of the mantle. It is solid and rigid, just like the crust. Rigid means stiff, okay, stiff and solid and strong. The uppermost mantle has a density slightly more dense than the ocean crust. It's 3.3 grams per cubic centimeter. Now, earlier I just told you the average density of the entire mantle, that would be the uppermost mantle, the upper mantle, and the lower mantle together. If you average out the densities, it comes out to about 4.5 grams per cubic centimeter. But just looking at the uppermost mantle, we're talking about slightly more dense than the ocean floor. But this is why it lays below or sinks below both the continental and oceanic crust. It's more dense. So as I said, the uppermost mantle is very, very important because together with the crust, it makes up this nice little section of planet Earth we call the lithosphere. And that word comes from a Greek word, lithos, which means stone. So I want you to think of the lithosphere as the solid rock sphere of planet Earth that actually is broken into huge sections that we call tectonic plates. And this is where we're heading. We're going to learn everything about the tectonic plates. And I want you to think of tectonic plates for now as very similar to the cracked pieces of a hard-boiled egg, because that's really a good analogy to what Earth's lithosphere might look like if we could view it from, say, outer space, just the lithosphere, take all the water off of the planet and look at the solid rock section of planet Earth. It's actually cracked. It's not smooth all around into these giant pieces that scientists call tectonic plates. And that word comes from a Greek word called tecton. Tecton means to build. So tectonic plates and what happens to these tectonic plates or the interactions between them, they actually are responsible for building the lithosphere that we live on. More on that later, but that's where we're heading here. So quick review. uppermost mantle, thickest section of the, the thinnest section of the mantle located right underneath the oceanic and continental crust, together with the crust, makes up the section of our planet called the lithosphere. Very important. That lithosphere is broken into those pieces we call tectonic plates. Now, right underneath the lithosphere is a very important section of the mantle called the upper mantle. Now, the upper mantle is a very, very cool section of planet Earth because the rock is solid, but it's plastic-like. Now, what do I mean by plastic-like? So in my hand, I have some pink silly putty. And silly putty is really cool and kind of therapeutic to play with. I can pull the silly putty and it will flow and move just like a liquid. But it's really a solid because I can break it like a solid. All right. I can roll it into a ball like a solid. But if I let it sit on my desk or in my hand for any amount of time, what will end up happening is that silly putty will flow out and flatten out. And this is called really pretty much a semi-solid. It's plastic-like. It is both solid and like a liquid. We believe that the upper mantle rather, the rock of the upper mantle might be very similar to the consistency of the silly putty. Solid, yet has this ability to move ever so slowly like a liquid. And that's a really important description. The upper mantle is denser than the uppermost mantle, and that makes sense because where does it lie? It lies below the uppermost mantle. It has a density of about 4.4 grams per cubic centimeter. So you see we're going from 3.3, we're getting a little bit deeper into planet Earth. The density is increasing. So we've got more dense peridotite down in the upper mantle. But this peridotite is solid and has this really unique ability to flow. Now, this is where the upper mantle gets its name asthenosphere from. The asthenosphere is an area of planet Earth, it's the alias for the upper mantle, that has this kind of semi-solid plastic-like rock. And astheno means without strength. And that whole description as without strength actually comes from this unique plastic-like ductile rock that we believe makes up the asthenosphere. And we'll talk about how we know this in a future lecture, maybe next week, really. And but scientists are pretty uh, know this pretty well, all right, that the rock is definitely behaves differently than absolute rigid rock. And we look at how seismic waves or earthquake waves behave as they travel through the planet. And I really will highlight that in, as I said, a future lecture. Now, what's really important about the asthenosphere, this plastic-like rock, because it has this ability to move, it actually, we believe, does move, and we believe it's flowing. So this solid rock is moving almost like a fluid in something we call convection currents. Now, I've put a picture of a lava lamp in my slide here, and I don't have my lava lamp moving behind me tonight. I will put it on tomorrow morning and make sure it's flowing for my next lecture for you. That lava lamp has been moving behind me for the last 7 weeks for a reason, because I'm building up to this. The lava lamp, I want you to think of the lava lamp, what's going on in the lava lamp. We have this up and down motion of that lava, which isn't really lava, that material that's in the lamp. I want you to think about what's causing that up and down motion. Because what's happening in that lava lamp, we believe, is very similar to the process that is happening here in the upper mantle with this up and down and all around motion. That motion is called convection. In today's activity, you're really going to learn a little bit about convection as you participate in a gizmo simulation. I'm not going to tell you too much right now on convection because I want you to discover what convection is with the gizmo, and then we'll really review. But I want you to think lava lamp, all right, in your mind's eye. Oh, we've got this flowing. Oh, it's called convection, just like a lava lamp. The gizmo is really going to take you through all of the science behind it. So that's the upper mantle. The upper mantle has plastic-like rock. It's solid, but it has this very unique ability to flow, very similar to silly putty. It's called the asthenosphere or asthenosphere. That's the alias for the upper mantle. It's the same thing. So when I say asthenosphere, think upper mantle. It is an area of planet Earth that sits right below the lithosphere. It sits right below the lithosphere. It's kind of like a gooey mantle, and it is flowing. Remember that. The asthenosphere flows. The lithosphere that sits on top of it is broken into huge, giant tectonic plates. It's very solid. And the last section of the mantle is the lower mantle. And the lower mantle, I don't want to tell you it's unimportant, but it kind of is for our study. There's a little funny from me, but I do want to review the lower mantle. The lower mantle for if we take a look at this picture, the lower mantle is absolutely the thickest section of the entire mantle. It takes up most of the mantle. So we have the uppermost mantle, very thin. The upper mantle, the asthenosphere, slightly thicker, but still thin. And then we got this big chunk of the lower mantle. The lower mantle is also called the mesosphere, the middle sphere. I think you're in the middle of the planet at that point. What I want you to remember about the mesosphere is certainly it's more dense than the asthenosphere that sits on top of it. By the time we get into the mesosphere, we have a density of about 5.7 grams per cubic centimeter. So the planet is getting much more dense, the material, as we dig further into planet Earth. And what's very interesting here with the mesosphere, kids, is although the planet gets much hotter the deeper we go into it, and we have an asthenosphere that's kind of semi-solid that sits on top of it, you might think that the deeper we go into planet Earth, that perhaps that mesosphere probably should be liquid because it's hotter and it's underneath the asthenosphere that's kind of like semi-solid, but it's not. And what's really cool about the lower mantle is it stays solid. And scientists actually really infer that it's staying solid because of that tremendous pressure of all of the layers on top of it. So think we're deeper into planet Earth, and then we've got the layers of the asthenosphere, the uppermost mantle, and the crust sitting on top of the middle or lower, the lower mantle, keeping it nice and solid. So for our study, we're really going to focus on the lithosphere, the uppermost mantle with the crust, broken into tectonic plates. And underneath that lithosphere, that gooey section of the mantle, which is solid rock but has this funky ability to flow, the asthenosphere. Those two sections of planet Earth are going to become very important for our understanding of the theory of plate tectonics. The last thing I wanted to briefly review, I gave you a cross-section of the planet, and this will not be the last time you see this. I'll keep on going over the cross-section. Asked you to label it based on some of the imagery I gave you in this Google Slides, and also from some of the other activities that you already completed for me in our study of the Earth's interior. The answer key, I'm actually going to work backwards. I'm going to work from the inside of planet Earth and work my way up because sometimes it's easier to really look at the planet that way, from the center to the surface. So at the center of planet Earth, for letter D, we are at what's called the inner core. Right above the inner core is a section of the planet called the outer core. And we're going to talk about the differences between the two next week very briefly. But in general, inner core is solid, outer core is liquid. All right. Right above those sections, here we have our different parts of the mantle that we highlighted in this activity. For letter B is referring to that section of the mantle called the mesosphere or the lower mantle. And again, you really look at this cross section, you can see it's the thickest part of planet Earth. Above that section, kids, I'm going to have you focus, and I used kind of like this gold arrow, is pointing to this letter E. E actually is showing you that E represents two parts of planet Earth, the crust and the uppermost mantle, this first little white layer of the mantle. That is the lithosphere. The lithosphere sits on top of letter C, which is the asthenosphere. And the asthenosphere, again, is that gooey section of planet Earth, the solid but flows like a liquid rock that has these nice little currents we call convection currents flowing in this area of planet Earth. On top of the lithosphere, or I should say, part of the lithosphere, not on top of the lithosphere. Part of the lithosphere would be the crust, okay? Because the crust is the uppermost section of the lithosphere. The oceanic crust, remember, is the thin section of planet Earth's crust, and it's located under the ocean water. So letter G represents the ocean floor, that thin section of the crust. And lastly, letter F represents the thicker section of the crust, the continental crust. So we have continental crust F, oceanic crust G. E represents both the uppermost mantle and the crust together, called the lithosphere. Very, very important. We're never going to talk about the uppermost mantle by itself. We're always going to talk about now the lithosphere, that section that's broken into tectonic plates. So the lithosphere is made up of two parts of planet Earth, the crust and the uppermost mantle together. Underneath that lies that semi-solid, plastic-like rock, the asthenosphere, followed by the lower mantle, also known as the mesosphere. And then as we get into deep planet Earth, we're at letter A, the outer core and the inner core. Okay, boys and girls, that's a nice little review of the mantle Google Slides. We are certainly by no means done with the mantle. Going on and moving further for today, you're going to participate in learning a little bit about what convection currents are, and then we're going to apply that to the asthenosphere. So we're going to come full circle and talk about the lithosphere and asthenosphere again, because they're very important as we build our beginning understanding of Earth's tectonic plates and actually what happens when these tectonic plates interact. Okay, kids, it's been real. Have fun.